my research is about estimating the variability of soil moisture in time and space within a paddock. In dryland agriculture, the amount of water available to grow a crop is determined primarily by in-season rainfall and the amount of water stored in the soil profile prior to sowing of the crop. To illustrate this variability, I've chosen a 90-hectare dryland paddock near Birchip in Victoria. This was part of research published by RAB in 2009. Several days prior to sowing, field samples were taken at 50 sampling locations across the paddock. Soil water content was measured at 4 different depths to describe the top 60 centimetre soil profile. The results were then mapped to show the spatial distribution of water content. The spatial variability of soil properties within an agricultural paddock or field is due to underlying geology and pedology, climate, topography and biological activity. There are many hundreds of single soil moisture probe rain gauge installations in paddocks across the southeastern grain belt of Australia. Single point measurements are inadequate to describe the variability of soil moisture within the whole paddock. The data needs to be interpreted carefully. Lack of sensors in the top 30 centimetres of the root zone limits understanding of the whole soil moisture profile. The soil moisture in the top 30 centimetres can be measured by using an ensemble-based approach of a hybrid soil-water surface energy balance model that assimilates data from remote sensing, climatic inputs and other data sets. The layer incorporating the crop and the soil surface can be measured remotely by optical sensors mounted on satellites, aircraft or UAVs, ranging from the visible spectrum and near-infrared to thermal infrared. These measurements, however, are adversely affected by cloud cover. The top 5 centimetre layer can be measured by active radar such as the Sentinel-1 satellite. These measurements are not affected by cloud or sunlight. The actual volume of soil measured by an 8-sensor probe, as illustrated, is approximately 13 litres. Again, emphasising the shortcomings of extrapolating single-point measurements to making management decisions for a whole field or paddock. Single-point measurement of rainfall with a range gauge has similar shortcomings. The small area of rainfall intercepted by a single rain gauge is about that of a small side plate of 17 centimetre diameter. This weather radar image of a local summer thunderstorm earlier this year illustrates rainfall spatial variability. Most of its rainfall occurred within a range of 30 kilometres. Intense rainfall during summer fallow is likely to increase because of climate change. The image shows the spatial distribution of rainfall, which is not indicated by the single point measurements from the official Bureau of Meteorology rain gauge network. Australia's climate is highly variable and small distances can result in large differences in the climate between a weather station and the field of interest. The rain gauge network of the Longrenong College data farm intercepted the edge of this thunderstorm with variable amounts of rainfall recorded by the adjacent rain gauges. The estimation of plant available water at sub-paddock resolution is achieved through the integration of a variety of available data sets. This is an example map of plant available water for a root zone profile at sowing. The development of management zones will assist farmers with improved on-farm management decision-making by modelling reliable and fit-for-purpose estimations of the spatio-temporal variability and availability of soil moisture at the sub-paddock scale. The prediction and measurement of plant available water is a key issue for estimating potential crop yield and consequently nutrient needs. Thank you.